We are going to study about spherical mirror in which there is some concept related with the focal length and radius of curvature. So let us see how these two terms are related to each other. Spherical mirror, a mirror whose reflecting surface is a part of a sphere. One side is painted and other side is made shiny. So we first take the in case of in case of a concave mirror. First of all, we draw the diagram here. Yes, just painted surface is shown here by showing the all different bar lines. The shaded lines shows that there is coating of the mirror. Yes, and give the name of the mirror M and M dash. The rule is that first of all choose the point P which is called pole of the mirror. P is the pole of the mirror and draw a straight line to make the principal axis. Yes, very straight line has been drawn here and this total concave mirror is supposed to be the part of the sphere. So dotted line shows the sphere's spherical surface and C is taken as the center of the sphere. Center of curvature is defined as the center of the spherical mirror of which given mirror is a part. So when you allow the light to incident on the mirror, what happens then? You draw the straight line as a ray of light. Yes, give the arrow sign and suppose this light is coming from the point A, source of light, and B is the point where the light incident on the mirror. And we know that when ray of light is parallel to the principal axis and when it incident on the any one point of the concave mirror, it bounces back and passes through a particular point which must lies on the principal axis. So between the P and C, there is another point from where the ray of light passes. Yes, this is the reflected rays. Give the arrow sign here once again. And we join the line of the point C to the point where ray of light is incident and bouncing back. B is the point from where the light bounces back, passing through the point called focus of the concave mirror. So in the case of concave mirrors, the remarkable point is that M and M dash is the total size of the mirror and AB is the incident light. AB is the incident ray of light. B to F is the reflected rays. reflected rays. XCP is the principal axis. Principal axis. Now, when we join the point C, center of curvature, to the point B, where the light incident and gets bounced back, this dotted lines is known as here normal to the plane, normal to the point B of the concave mirror. And this normal is CB. You may imagine that this is the normal. And I is the angle made by the incident light with the normal, and R is the angle of reflection made by the reflected light with the same normal. Now, the relation between focal length and radius of curvature. How to find the relation? We know that here C is the point of center of curvature and P the point of pole. The total distance of the P and C is here taken as radius of curvature. So, right first, P to C is taken as R, radius of curvature, radius of curvature, and P to F is equal to focal length of the mirror, focal length of the concave mirror, and relation between these two is that F is equal to R by 2. How to prove this relation? How to prove this relation? Proof of this relation is that with the help of this ray diagram, we will prove the relation. So, A, B, and C. AB is the incident light. C to B is the normal. How to write I and R? A, B, C, angle at B is angle of incidence I, angle of incidence I. This very I is equal to CBF R according to the law of reflection. So, by taking care of the position of the point, C is the center of curvature, B is the point of incidence, and if the ray is passing to the F, so CBF is the angle of R, angle of reflection. And by using laws of reflection, laws of reflection to the concave mirror by writing I, which is always equal to R. So, in the case of reflection through the concave mirror, the inside the triangle, uh, inside the triangle, the ray AB is parallel to the XCP, so I also becomes at the point C. So when angle I and angle R are equal to each other, then distance of the CF and distance of the BF point are also equal to each other. So we will take care of the point I is R. So B to F point is equal to C to F point due to the reason that the two angles are equal to each other in at triangles. So it is seen here that the CF distance and VF distance are equal to each other, and B is taken as any one point where light is incident. It may be near to the pole. So distance of the B to F and distance of the P to F are also equal to each other. So by choosing B to F is very close to the pole, so it is also equal to P to F. It means we take the distance C to P as C to F and add it to the P to F. And C to F is nothing but it is equal to what? C to F and P to F. C to F, C to F and B to F and P to F all are equal to each other. So write here the value of CF, which is equal to BF and PF. BF is also equal to PF and this is also equal to PF. We get the value twice of the PF. And what is our value of PF? PF is equal to the focal length of the mirror. So C to P is the distance of radius of curvature. We write for capital R and it is 2 times small f. So ultimately we get the relation for focal length in terms of half of the radius of curvature. So mathematically it is very easy to find by making use of the ray diagram and we get the required relation.